In this video, I would like to show you how to represent a longitudinal sound wave that has a frequency of 500 Hertz. This particular sound, we are going to only represent two full wavelengths. We can represent more, but in a test or an exam we would probably ask you to represent two, maybe three at the most. We are also going to ask for a fully labeled sketch, and albeit that sound travels in 3 dimensions, we are going to represent it 2-dimensionally. So if, for instance, you have a speaker that is vibrating backwards and forwards, as I have here, then the sound that is produced is going to move out into 3-dimensional space like that. We, however, for the purposes of the sketch, are going to represent a small section of the sound wave in that box. Personally, I like to start with the source, so I'm going to represent the source by a loudspeaker that has a membrane like that. You'll have to excuse me, I am not an artist, but rather a science teacher. And I'm going to represent the fact that this membrane vibrates backwards and forwards like that. Now, as this membrane vibrates backwards and forwards, it's going to pressurize, it's going to compress the air, which is the medium, and it's going to rarefy it. So it's going to compress and stretch and compress and stretch. Now, I'm going to start off with a region of compression. So I'm going to draw it like this. So there's a region of compression. These are little wave fronts that would represent lots of air particles all moving in the same direction at the same speed. This would be a region of compression. This would be a region of rarefaction, where the pressure is less. It's where the speaker has stretched the air. There's a region of compression. There's a region of rarefaction. Another region of compression. So I'm going to represent with a C the region of compression, a region of compression. So these would be regions of compression, and regions of rarefaction by R. Now, this region of compression was formed here at the vibrating membrane before this one was and before that one was. And the reason we know that is because of the fact that the propagation of this wave is to the right. And the velocity of this wave is the velocity of sound, which is approximately 340 meters per second in air. The same is true of the regions of rarefaction. This region was created earlier than that region was. So when a compression zone is formed, the membrane pushes forward, pushes to the right on the medium, which is air, and when increasing the pressure of that region, and when a region of rarefaction is formed is when the membrane, vibrating membrane, moves to the left, almost sucking on the air, reducing the pressure in that region. Now, if we look at the membrane, the membrane is the source. So it's good to put the source there. And as I've done, shown that there is a vibration there of the membrane. We could have used regions of rarefaction, as you will see now, to represent two wavelengths, because a wavelength is the distance between two successive points that are in phase. Now, if we look at the center of a region of compression, there would be air particles that would be moving like that. If you were to look at them over a period of time, all the air particles in this medium would be moving backwards and forwards. Because this is a longitudinal wave, the disturbance is to the right and to the left, backwards and forwards, to the right and left, to the right and left. And the velocity of the wave is to the right. Therefore, this is a longitudinal wave. But if we now look at these particles that are, if you want to call it a wave front, in the center of the region of compression, then let's take these two particles. Then the distance between them would be one wavelength. So I'm going to take that distance there. I just want to change the color. I'm going to take that distance there and that distance there, and that would be one wavelength. We represent it with lambda, because a wavelength, as we've defined it, is the physical distance between two successive points in phase. This, if we looked at another air particle moving in phase with these two, and by in phase we mean they're moving in the same way, at the same speed, in the same direction, at the same time, then we find that this would also be one wavelength. But now, if we were to go to a particle in the center, if we had to go to, let me just represent it like this. If we were to go to a particle in the center of a region of rarefaction, and then a successive one wavelength on, then this too is one wavelength. So the easiest way to represent wavelengths on longitudinal wave diagrams is to either go to two successive centers of regions of compression and draw in the distance, or the centers of two regions of rarefaction and draw in the distance. Now, we've yet to work out the actual magnitude of the wavelength. We'll do that shortly. But we were asked here to draw this wave, and we could have two wavelengths of this wave. We could have done it starting with this region here, and then have had three regions of compression and three regions of rarefaction and two included regions of compression, and that would have constituted two wavelengths. As a personal matter of choice, I prefer to work with regions of compression, but it doesn't make a difference. You would get the same marks whichever way you did it. So let's now work out, because it says it must be a fully labeled sketch, we're also going to put in the values. So in order to work out the value of the wavelength, we need to work with and I'm going to reduce this a little bit here to give us some space. We're going to work with V v equals f lambda, which is the classical wave equation. The velocity is 340 meters per second. We were given that the frequency is 500 hertz. And so we want to work out lambda using our calculator. We divide 340 by 500. And that gives us a wavelength of 0.68 meters. So you would do well to put that into your diagram. And albeit that we haven't explicitly asked that the period be shown, it would be wise to do it. So we're going to do that. We're going to say, well, okay, the period is going to be 1 over the frequency, which is 1 over 500 hertz, which is going to be 0.002 seconds. So we could represent this as follows, just in brackets, saying t is 0.002 seconds. And what that actually means is that, and I'm going to open this up here, if you were able to have a magic eye and you looked at this point there and you had a stopwatch, you wouldn't put this into your diagram, obviously, I'm just explaining now, then the time it would take for the next, we're looking at the front of the compression region, the time it would take for the next front of the next compression region to come through would be 0.02 seconds. Another way to look at it is to look here and to say, well, okay, for one full vibration, it would take 0.002 seconds for this membrane to vibrate like that back to its original position. Keep in mind that the frequency of the wave is always equal to the frequency of the source, as long as the source and the receiver or listener are not moving with respect to each other. Because if they are, this leads to another phenomenon, which we'll study later on in grade 12, called Doppler shifting. So coming back now to the diagram, if we look at the diagram in its entirety, we can see now that there is a fully labeled longitudinal wave diagram, and I see that up at the top here I have spelt wave incorrectly. I've said or, but you know what, it absolutely is awesome. Physics is awesome. So keep in mind that this section that I've shown you here, that we've represented, is in actual fact only a small slice of the total sound wave that goes out into 3 dimensions. I hope that this has helped you with what is often a very challenging question to answer in an examination.